Hello, everybody, and welcome to Chapter 2. Again, I wanted to take just a couple minutes and sort of drill down to one of the concepts that tends to be more challenging in this chapter, and this is the concept of heat transfer through radiation. So we talked about heat transfer through conduction and convection. The transfer of energy from one object to another by radiant energy or radiation without the space in between being heated is radiation. So radiation travels in waves, all right, travels in waves that release energy when those waves are absorbed by a different object. So when heat is created by an object, whether it's the sun or a red hot piece of steel, the radiant energy travels through space without heating space, and then that energy is released when another object absorbs that radiant energy. So these waves, they have electrical and magnetic properties, and so they're called electromagnetic radiation. And they don't need a medium to propagate through. Think about the sun. It emits tremendous amounts of radiation at all wavelengths of the electromagnetic spectrum, but space is a vacuum, and space is not heated up by the sun. The Earth is heated by the sun. So all that energy is created by the sun. The radiation travels 93 million miles across an empty void of space, and then when the energy strikes the sun, when the energy strikes the Earth and the Earth absorbs that radiant energy, that's when the heat is released, and that's when the Earth heats up. So electromagnetic waves do not need a medium to propagate through. All matter absorbs and radiates energy. So you are radiating heat. You're not radiating light. We don't shine, but we do reflect light. But we radiate heat. Your desk that you're sitting at radiates heat. Of course, the sun radiates heat. It also radiates light. Other stars radiate light. The moon, it's very cold. It radiates some heat, but it shines. It doesn't radiate light. It doesn't create visible light. And visible light is part of the electromagnetic spectrum. So everything emits radiation. Everything absorbs radiation. So if you're sitting next to somebody and you can feel their warmth, that's radiation being emitted by that person and being absorbed by yourself. Now, the waves that radiation travels on have a distance between each peak or each crest, and that distance is the wavelength. And the distance of the wavelength is very important to understanding how radiation works. And what's very important about this concept is radiation that has longer wavelengths. So radiation with longer wavelengths carries less energy than radiation that has the shorter wavelengths. So radiation with shorter wavelengths carries more energy. So what does that look like in reality? A wavelength is something like this. Let me change that to this marker. So this is my wave of radiation, all right? And that has a very long wavelength. There's a lot of distance between here and here, and that longer wavelength carries less energy, all right? Where a shorter wavelength is going to carry a lot more energy. So a very short wavelength, lots and lots of crests and peaks. That shorter wavelength is going to carry more energy. All right, so this is what that looks like. These are the different types of radiant energy. You have everything from X-rays. Now you think about the space movie and this Martian shooting you with the laser gun. It's going to be an X-ray gun, right? He's not going to shoot you with an AM radio gun. He's going to shoot you with an X-ray gun, because an X-ray has an extremely short wavelength and carries a tremendous amount of energy. That's why when you have X-rays done, you have to cover sensitive parts with lead, because the X-ray can actually do damage, and that's why you don't want to have too many X-rays, because X-rays carry a great deal of energy and they can do damage. The next on this on the energy spectrum, so here are my X-rays, very short wavelength, a very short distance between here and here, lots and lots of energy, big time energy. The next EM, electromagnetic wavelength that we're going to talk about, is ultraviolet. Ultraviolet also has a short wavelength and a lot of energy. And of course, we protect ourselves from ultraviolet rays as well. The ozone protects us from ultraviolet rays. Without the ozone, life couldn't exist on the surface of the planet, because ultraviolet rays would just burn us to a crisp. So ultraviolet rays have a very short wavelength and carry a lot of energy. Visible light, and that is all the light that we see from red to violet. Violet on the short end and red on the longer end. All that visible light, altogether known as white light, all that visible light has fairly short wavelengths. Infrared has fairly longer wavelengths. It actually carries less energy, which is not quite intuitive because we can feel infrared energy. Infrared energy is actually heat, but infrared has a longer wavelength, and then as you go up, longer and longer wavelengths. So you think about a television tower in the middle of a city. We don't need to protect citizens from television wavelengths because they have very long wavelengths. But AM radio also very long wavelengths. So radio frequencies typically don't carry enough energy to be harmful. All right, now that concept of the amount of energy and the wavelength are tied together by two different laws and two different mathematical equations. And I want you to understand the concept here. We're not going to actually solve any of these equations or work any of these equations, but I need you to understand the two concepts. And the two basic concepts are that the wavelength where the maximum amount of energy is being emitted, so the wavelength of maximum emission where the most energy is being emitted from any object, is equal to C, which is a constant, divided by its temperature, is equal to C divided by its temperature. So the higher the temperature, think about this, the hotter the temperature is, the higher the temperature, the shorter the wavelength. Short wavelengths carry more energy. So the hotter the temperature, the more energy is being carried. And that makes sense. If I have a piece of steel and it's cold, I can grab it. It's not giving off a lot of energy. But if I heat it up to 1,000 degrees and it's glowing white hot, if I grab it, what is it going to do? Release tremendous amounts of energy and burn me. So again, this first law tells us that the wavelength of energy, that the wavelength, maximum wavelength, where the object is emitting most of its energy, whether it's the sun or the earth or me or your desk, the wavelength at which that object is emitting the most energy, that max wavelength, is inversely proportional to the temperature, meaning as the temperature goes up, that wavelength goes down. As the temperature goes up, that wavelength goes down. And we also know that short wavelengths carry a great deal of energy and long wavelengths carry less energy. So something that's very hot is going to emit radiation at a shorter wavelength, and that radiation is going to carry a great deal more energy. So hot objects emit a great deal more energy, and that should be intuitive because hot objects can burn us. Now, that law is based on a law known as Wien's law, or sometimes Wien's displacement. And Wien is a scientist who came up with this concept, and he came up with this this constant. And what Wien's constant tells us is if we know the temperature of an object, we can know the wavelength at which the object is emitting most of its energy. The opposite applies. If we can figure out which wavelength the object is emitting most of its energy, we can figure out how hot the object is. And by knowing what energy arrives at Earth, what energy, the most energy arrives at Earth, we know how hot the sun is. Right? The second law, two different scientists, Stefan and Boltzmann, and they come up with the Stefan-Boltzmann law, and this is a direct relationship. So this relationship up top, the Wien's displacement, is an inverse relationship, where as temperature goes up, as temperature goes up, the wavelength goes down. And we know as a wavelength goes down, the amount of energy goes up. So that's an inverse relationship. This is the direct relationship. And this is also a constant. Sigma is 5.67 times 10 to the minus 8th Weems per kilometer squared. Anyway, this is the constant. And so what this is actually telling us is the amount of energy being released by an object is directly proportional to its temperature raised to the fourth power. So if you double the temperature, you don't double the amount of energy, you double the amount of energy to the fourth power. So that tells us as temperature goes up, the amount of energy being released is tremendously gets significantly higher very, very quickly. Again, intuitive. The sun is very hot, and the sun gives off a great deal of energy. The sun is very hot, and the sun gives off a great deal of energy. And so this law is the amount of energy is directly proportional to the temperature raised to the fourth power, and that is the Stefan-Boltzmann law. All right, tying these things together, what that tells us is that the sun Wien's law tells us that if the sun, which is very hot, 6,000 degrees Kelvin, the sun is very hot, 6,000 degrees Kelvin, then the wavelength that is emitted by the sun will be short. Since the sun is very hot, the sun will emit a short wave radiation, and that short wave lies mainly within the visible spectrum. So what we know, what Wien's displacement law tells us, is that of all the energy, the radiant energy, the radiation the sun puts out, most of it is in the visible spectrum, and then less of it is in the infrared spectrum. So most of it is light. It's the radiant energy of the sun. I'm going to draw a sun and draw my bright light. Most of it is the light that comes from the sun. Hang on, we'll put a happy face on the sun. Most of it is the light, and much less of it is the heat that comes from the sun. And that, again, is somewhat, that's a terrible A, but that's the heat. That's somewhat intuitive, because here's the sun, and way out here is Pluto. Well, you can see the sun from Pluto. The light arrives at Pluto, but you barely get any of the heat there, because the sun puts out a tremendous amount more visible light than it actually puts out heat. And that's because the sun is very hot. And because the sun is very hot, it puts out most of its radiation in a short wavelength, and it happens to be in the visible spectrum. The shortest wavelengths of light are the violets, and then of course ultraviolets next to it, and the longest wavelengths of light are the reds, and the infrared is next to it. So the sun's radiation is a short wave, so solar radiation is referred to as short wave radiation or incoming short wave radiation, sometimes called insolation, and we'll refer to insolation pretty much for the rest of this class. The sun's energy is insolation. All right. Next, come on. Just trying to get this to advance. Hang on a second. There you go. All right. So Wien's law also tells us that since the Earth is cool, only about 288 degrees Kelvin, then the wavelength of its emitted radiation will be long and lies within the infrared spectrum. So looking at this diagram again, we see most of the sun's radiation is between 0.4 and 0.7 micrometers. It's a very short wave. That's where the sun, with a 6,000 degrees Kelvin temperature, emits most of its radiation. And the Earth, at 288 degrees Kelvin, emits most of its radiation between 5 and 15 micrometers. So this is 0.4 and 0.7 micrometers, and the Earth is between 5 and 15. So Wien's law also tells us that since the Earth is cool, then the wavelength of emitted radiation will be long and lies in the infrared. So the Earth does not shine. It does not give off white light. It only radiates heat. The radiant energy from the sun travels through space. It strikes the Earth absorbs it, and then re-radiates, not light, but heat. Earth's radiation is sometimes referred to as terrestrial long-wave radiation, or sometimes outgoing long-wave radiation. But what's important to understand is the sun's radiation is short-wave, and the Earth's radiation is long-wave, and that has a huge impact on what we know as the greenhouse effect, because greenhouse gases, including carbon dioxide and methane and nitrous and ozone, those gases do not absorb short-wave radiation. The atmosphere is largely a window to the short-wave radiation. The sun's radiant energy travels through the atmosphere. It's absorbed by the Earth absorbs that energy, then re-radiates it as heat, but those greenhouse gases readily absorb those longer wave radiations, that longer wavelength of heat, and those greenhouse gases will absorb those longer wavelengths. And that's what keeps the atmosphere warm. And it's necessary. The greenhouse effect is very necessary. Without the greenhouse effect, the Earth would be much, much, much colder. All right, and this is how this works. Now, there's a lot of information here, but basically what you're looking at is all these different gases that we know as greenhouse gases: nitrous, methane, oxygen, and ozone. Water vapor is the most important greenhouse gas because there's so much of it, and it's variable from place to place. Carbon dioxide, we all hear about that. This is the sun's, on all of these, this is the sun's wavelength of maximum emission. That's that visible light. And largely through all these gases, the atmosphere acts as a window. Largely, none of those gases absorb those short wavelengths. A little bit here in oxygen and molecular, oxygen and ozone, but nitrous, methane, water vapor, carbon dioxide, essentially act as a window. It all goes right through the atmosphere. But once the Earth absorbs it, here's the Earth, it absorbs it and then re-radiates those longer wavelengths out, we can see that nitrous and methane and molecular oxygen and ozone and water vapor, to a significant degree, they absorb those longer wavelengths. Those greenhouse gases and carbon dioxide absorb those long wavelengths of radiation. So this last little one here at the bottom sums up all the gases. So most of the energy comes through the atmosphere, and those longer wavelengths are then absorbed by the atmosphere. And the text here to the left basically explains that to us. The gases in the atmosphere are known as selective absorbers. They only absorb and then re-emit at certain wavelengths. The sun's incoming shortwave radiation, that insolation, passes through the atmosphere and is absorbed by the Earth, warming its surface to then be re-emitted as long-wave radiation. The Earth emits long-wave or infrared radiation that is absorbed by those selective absorbers, which are warmed. And once those gases are warmed, they warm the air around them, and this is important, they re-emit long-wave radiation to be absorbed by other gases in the Earth. So those selective absorbers do not absorb the short-wave radiation coming through. They absorb the long-wave radiation going out. And because they absorb the long-wave radiation going out, they are warmed, and they warm the atmosphere around them, and they re-emit long-wave radiation to warm other gases and the Earth as well. The selective absorbers are the greenhouse gases, of which water vapor and carbon dioxide are particularly effective, and water vapor is the most important because there's just so much water vapor out there. It makes water vapor the most important. As selective absorbers absorb and radiate infrared radiation, they act as an insulating layer around the Earth. And that's extremely important. As those selective absorbers absorb long-wave radiation, they act as an insulating layer around the Earth. And that's what this looks like. The shortwave radiation passes through the atmosphere, okay? Passes through the atmosphere and warms the Earth, all right? Warms the Earth. Without an atmosphere, with no atmosphere, all of that outgoing terrestrial radiation will be escaped to space. It would all escape to space. And without an atmosphere, the Earth's temperature will be about 0 degrees Fahrenheit. So if absorbed, insolation and emitted terrestrial radiation are imbalanced, then the Earth has reached its radiative equilibrium of 255 degrees Kelvin. Okay, that's 0 degrees Fahrenheit. The difference between the 255 and the 288, which is the actual temperature of the Earth, is the Earth's atmosphere, which is a selective absorber and creates the greenhouse effect. So I'm going to go ahead and go through this again. With no atmosphere, all the shortwave radiation comes in, and when they go back out to space as long-wave radiation. With the atmosphere, the shortwave radiation comes in, and the long-wave radiation goes out, but it's absorbed by the atmosphere, where the atmosphere is heated, and we re-emit more long-wave radiation. We warm the atmosphere around us, and it creates a greenhouse effect. And the difference between no atmosphere is 0 degrees Fahrenheit, not Celsius, but Fahrenheit, so 32 below freezing, and 59 degrees Fahrenheit. So with our atmosphere, we're at about 59. Some scientists actually say now we're closer to 60 degrees Fahrenheit. That's the global warming you hear about. But with that atmosphere, we're at 59 degrees Fahrenheit warmer, significantly warmer. That is the greenhouse effect. And you can see why those greenhouse gases, therefore, are so terribly important to us. So the atmosphere does not readily absorb shortwave radiation, the region from which the sun emits most of its energy. Most of that energy just goes right through the atmosphere. So the atmosphere does not readily absorb shortwave radiation, the region from which the sun emits most of its energy. Insolation passes through the atmosphere to strike the Earth's surface, okay, warming the surface. Air molecules in the first few centimeters are warmed how? By conduction. As warm air becomes less dense than the air around it, heat is transferred upward how? By convection. So incoming solar radiation comes in, it heats the Earth, a little bit of the atmosphere is heated up, and convection heats the rest of the atmosphere. And those are the convection cells. It goes up, it cools off, and it drops back down. All right, we want to get more into what's going on with latent heat and how latent heat affects the atmosphere, and you can find that in the narrated lecture for Chapter 2.